Oh, good afternoon everyone, Dr. Bennett here. So welcome to the final video of this series about the Breguet range and endurance equations. So in this final video we're going to look at a derivation and analysis of the Breguet range equation specifically for a jet-powered airplane. So as with the previous videos in this series, we're going to start with the average value method to start our derivation. In this case, the average value method for the range is just simply the airspeed multiplied by our endurance. So for example, let's just have a quick look at the units here. If we've got an endurance defined in hours, let's say, and we have an airspeed in knots, which is nautical miles per hour, then the units of this equation will be nautical miles per hour multiplied by hours, and that will give us a range in nautical miles, for example, which is what we want. So we saw in the previous video that the endurance term here, E, is just given by the amount of fuel that we have to burn. So this is our fuel load, delta WF, divided by the rate at which we're burning it. So WF dot here is just the derivative of WF with respect to time. And again, we said previously that the rate of fuel burn is basically a feature of how the engine performs. In the case of a jet-powered airplane, the thrust-specific fuel consumption is equal to the rate of fuel burn divided by the thrust output. And so if we're in a cruise condition where we are at constant speed, then the thrust will be equal to the drag, right? So basically what I've done here is I've just replaced WF dot here in the denominator with CT multiplied by T, and then use the assumption that thrust is equal to drag. So that gives us our starting point for our Breguet range equation derivation. So here, basically what we're going to do is integrate this equation between two specific weight stations, W1, which is our starting weight, W2, which is our ending weight, instead of using this delta WF term in the numerator. So what we're going to do here is basically follow this through, perform this integration, and that should lead us directly to the Breguet range equation for a jet. So as with all of our previous videos in this series, our first little trick to get us started is to multiply by 1 in disguise. So if lift is equal to weight in our cruise condition, constant altitude, right, then lift over weight is equal to 1. So we're going to multiply by 1 in disguise in this equation. U1, W2, then let's write this as 1 over CT, L over D, V over WD, W. Now, the reason why I've grouped the terms like that is so that we can basically isolate and then take out the terms that don't depend on W outside of the front of the integral. So let's just do that real quick. 1 over CT. Convert our magnitudes of lift and drag into coefficient form. I can do that because they're both non-dimensionalized with respect to Q and S. And then inside the integral I'm left with V over W dW. So why didn't I take out V from the integral? Well, as we've said many times so far in this series, and the reason why we're going to extrapolate this average value method into something slightly more robust is because V depends on W. We go back to the lift equation. L is CLQS. So using our expansion for the dynamic pressure Q, 1/2 rho V squared, where in a cruise condition lift is equal to weight, we can see that V is a function of W. So as the weight of the aircraft changes, as we burn fuel in our range flight, then the speed at which we should trim the airplane at in order to achieve maximum range also changes relative to the weight. So we've seen this equation before, v 2w over rho SCL square rooted. So as the weight reduces, the speed should also reduce to compensate to achieve maximum range. So that's why we can't take the v term outside of the integral, is because it's a function of w. So let's go ahead and replace this expansion for v into here. 1 over ct, cl over cd, w1 to w2. So then let's see, 2w over rho SCL over w, square root all of that, dw. So that looks like a little bit of a mess, but we can simplify this and take out all of the other terms again that don't depend on w. So I can take out the 2, the air density, wing reference area, and CL all out to the front of the integral. And that will give me the following. So 1 over ct, I'll have a CL to the half, right, because I've got CL to the half in the denominator inside that I'm going to bring out. And then I've got square root of 2 over rho S, I believe, at the front. And then inside the integral now, I should have a square root of w in the numerator over w in the denominator. So that will just give me 1 over the square root of w, or if you prefer, w to the minus half. So finally, we're in a position now that we can actually go ahead and perform this integration. Should be straightforward now. So let's just do that real quick. 1 over ct, let's copy this stuff down at the front, 2 over rho s. Then the integral of w to the negative half with respect to w, add 1 to the power, divide by the new power. Divide by a half, so like that. W2, W1. And so applying the limits of integration and taking out this factor of a 2, let's say negative 2 over ct, cl to the half over cd, 2 over rho s, square rooted, and then we're going to get inside this bracketed term at the end, w2 to the half minus w1 to the half. Or if you prefer to push this negative sign inside the bracket term, we will get simply range is 2 over ct, cl to the half over cd, 2 over rho s square rooted, and then flipping that bracketed term. So pushing this negative inside of here, w1 to the half minus w2 to the half, or the square root of w1 minus the square root of w2. And that there is the Breguet range equation for jet-powered airplanes specifically. So a little bit more of a complicated equation this time, so let's just have a quick look at some of the terms. So if we are interested in maximizing range, we need to first of all minimize our thrust specific fuel consumption. That makes a lot of sense, hopefully. I mean, intuitively, if we minimize our fuel consumption, thrust specific fuel consumption, then we're going to be able to eke out the maximum amount of range. We'll come back to this term in a second because we have a little bit more analysis to do on that lift to drag ratio right there. in this term, we need to minimize the air density to maximize range. So minimizing air density, that tells us that flying at a higher altitude will give us a better range for a jet-powered airplane. And also minimizing our wing reference area. So that's, a larger wing reference area is going to generate more drag and therefore reduce our range. So the minimum amount of wing reference area that we can get away with while still producing enough lift to maintain altitude, basically, is what we require here. And then in this final bracketed term here, if we maximize our fuel load, that's going to maximize this term here in the brackets and therefore maximize range. So let's have a quick look then at what to do about this term right here. So that's not a direct lift to drag ratio. We have CL to the half over CD. So max range is found when CL to the half over CD is maximized, right? So maximizing this term will maximize this. And that is mathematically equivalent to minimizing the reciprocal. Right, all I've done is flipped it and minimized it instead of maximizing it. And the reason why I've done that is because I know how to find the minima of a function. I can find the derivative and then set it equal to 0 and solve. So what I'm essentially going to do is do d CD over CL to the half by dCL and set it equal to 0. And that will give me the minima of that function. So let's just do a quick expansion just to make this a little bit more straightforward. CD over CL to the half, if I do an expansion for the total drag coefficient as the parasite drag coefficient plus CL, KCL squared, which is the induced drag part, and then CL to the half in the denominator, and just tidy that up a little bit to the half, just splitting this up, K CL to the 3 halves, right? Then that's just going to make my differentiation just a little bit more straightforward. So therefore d CD over CL to the half by dCL will be the derivative of this plus the derivative of this. So the derivative of this with respect to CL is minus a half CD naught over CL to the 3 halves, right? Bring the power down, take 1 from the power, and then the derivative of this, easy, bring the power down, take 1 from the power. And I'm going to set that equal to 0. So therefore, just dealing with this, I can take this term to the other side. So I'm going to get this and if I multiply everything by 2 and also multiply everything by CL to the 3 halves, I will get the following: 3K1CL squared is equal to CD naught. So what does that actually mean? Well, if we remember that this is our parasite drag coefficient, this is our induced drag coefficient, this tells us that maximum range is obtained when the parasite drag is 3 times larger than the induced drag. We have to multiply the induced drag by 3 to make it equal to the parasite drag, and that's a very interesting result, and it's a relationship between the two components of drag that we haven't yet seen before. And it's actually opposite to the way in which this whole formulation works for a piston propeller driven airplane, just simply as a consequence of how those different propulsion types produce thrust. So that's a very interesting result, and one that we should keep in mind moving forward for some of our next topics. So that is the Breguet range equation for a jet-powered airplane, and basically how to maximize it and what conditions are applicable to it. So that wraps up this little mini series on the Breguet range and endurance equations. Thank you very much for listening, and we'll see you next time.